Welcome to Engineering State of Mind. Today, as promised, we are going to cover the first in a series of videos of how an aircraft flies, which shall address Bernoulli's principle and theory of flight. Let's get to it. What makes an aircraft fly? It all starts at the runway. We are cleared out for taxi. The pilot starts the aircraft. The engines rev up and onto the throttle. Off we go, cruising down the runway very fast. It does its thing. With a click of a button later, the aircraft is up in the sky. Now there, we are done. It's over. The plane's up in the sky. Everyone is happy. It's that simple. Or is it? Aha! If only. Now, jokes aside, it takes more than an engine running and magic to make an aircraft fly. Don't worry about the aircraft at the beginning of the video. It was meant to light up the mood. Stick with me and we shall make a better animation showing how a real aircraft flies with movable control surfaces and a retractable landing gear. We shall cover it to every minute detail as possible. Let's start with the forces acting on an aircraft in flight. There are four forces acting on an aircraft in flight. They are lift, weight, thrust, and drag. Lift is opposite to weight, and thrust is opposite to drag. Therefore, the sum of each opposing force is 0. This remains true as of Newton's third law, which states that for every action of force, there is an equal and opposite reaction force. When all forces are balanced, the state of the aircraft is a steady and level flight. When the plane goes upwards, therefore, lift and thrust are more than weight and drag. The opposite happens when landing, i.e., weight and drag are more than lift and thrust. Bernoulli's principle is explained practically by a Venturi tube, which shows movement of air and how velocity and pressure changes. Inside the Venturi is a constriction in the middle, and pressure and velocity is checked. In the beginning, as air is passed through the tube, the velocity and pressure are equal. As soon as air enters the constriction, velocity increases and pressure decreases. Once the air leaves the constriction, velocity decreases and pressure increases. This is how Bernoulli figured out that there is a pressure difference when air passes through a constriction. The upper part of the aerofoil acts as a constriction. Now, if we had X-ray vision, or were able to cut through a section of the plane, in our case, the pink part would be the aerofoil shape. The aerofoil is designed in a shape and way that aids in lift. In order to learn the aerofoil better, it is deemed necessary to know the parts. This is because we'll be mentioning some of the aerofoil parts as we move through the series. Parts of an aerofoil. Leading edge. This is the foremost part of an aerofoil. Trailing edge. This is the rearmost part of an aerofoil. Angle of attack. This is the angle at which relative airflow meets the aerofoil. It's measured between chord line and relative airflow. Chord. This is the distance between leading and trailing edge of an aerofoil. Chord line. It is a straight line that runs from the leading to the trailing edge. Relative airflow. This is the resultant of motion of an aircraft through the air. Camber. This is the maximum distance between mean camber line and chord line that is measured perpendicular to chord line. Mean camber line. It is that line that is imaginary that shows curvature of the wing. It runs from leading to trailing edge and has equal distance from lower to upper surfaces. Thickness. It is the thickness of the aerofoil, i.e. from the upper to the lower surface. On the aerofoil, due to the shape, the upper part has a longer distance to cover while the lower part has a shorter distance to cover, which creates an area of low pressure above and high pressure below. This pressure difference, together with the downwash brought about by streamline flow directed downwards, causes lift. If you like the content, don't forget to subscribe, like the videos, and please click on the bell for notification. Thanks again. See you next time.